Okay, well, let's get started. As always, don't forget the seating survey. The only assignment for this week is the homework that is due on Friday. We are planning to have a small group activity that is going to be due next week. And so I will have that up in a day or two. Do we have any logistical questions before I start getting into some content? No content videos this week. That's correct. I had some things going on this weekend, unfortunately, that kept me from getting any made. And so once again, this week, I am going to be on Monday and Tuesday, I'm going to be going over the content like I did last week. We have two main areas of content that we're going to go over. The first is basically sort of a catch-all set of details about acids and bases. And the second is a bit of a bigger topic, buffers. And so we'll be getting through both of those hopefully today. Tomorrow will be exactly the same thing for people who are not showing up for the Tuesday, Thursday classes. If we are not able to get through all of the content today, then I will extend into Wednesday and Thursday. Okay, so I want to review a couple of items because I was gathering that there was a bit of confusion about some aspects. There is a standard acid reaction form in aqueous systems. And that is this. Here, A can be any, HA is any weak acid. This is not necessarily something you should have to memorize. The idea of the standard acid reaction is that the acid is reacting with water. Because it is an acid, it is donating a proton to the water to make the hydronium ion. This reaction has an equilibrium constant that we call Ka, as the form A minus H3O plus over HA. Okay, now it's important to recognize here that labeling this as as HA does not necessarily mean that this is a neutral species. All we're doing here is saying that when we look at the charges here and here, we are going one more negative when we have it over here. So an example where this is the case would be something like H2PO4 minus acting as an acid like this. So the A here can be anything, including something that is charged. That's what's going on here. Similarly, when we write the standard base reaction, we have B aqueous plus H2O liquid in equilibrium with BH plus aqueous plus OH minus aqueous, where our equilibrium constant for this reaction is the BH plus over B, like so. This is not saying that B has to be neutral. So we could have, for example, NH2 minus plus H2O in equilibrium with NH3 plus OH minus. And so our B could be charged. All right. Does this make some sense? Any questions on our standard acid and standard base reactions in water? Okay. So, I mentioned this briefly last week in at least one of the classes, but I want to make sure each class session gets this information as well. There's a question about how do you know whether a particular acid or base is a strong acid or base or a weak acid or base. There are a couple of aspects to this. There aren't all that many common ones. These 6 of each are the most common strong acids and strong bases. In most cases, these, if you see something in a problem other than these 12 items, you're looking at a weak acid or a base. So simply keeping this list near you, or maybe even memorizing it to know which ones you're dealing with as strong acids or bases is somewhat useful. Of these, hydrochloric acid, nitric acid, and sulfuric acid are the most common of the strong acids. And of the bases, these top 3 are the most commonly used. Now, there is something we can do to compare strengths of acids and bases based on their structure, and we're going to look at that in a moment. First, this may not be very easy to see. Let me see if I can zoom in a little bit. Okay, so this is from the textbook, and what we have here is a ranking of acid strengths. They're getting to stronger acids as we go to the top. Notice that these are paired. So if we have the acid HClO4 on the left-hand side, this is its conjugate base on the right-hand side. And so that's true all the way down this list. And notice here that we have the hydronium ion and we have water in these places. And so those end up bracketing the weak acids that are in between. If we have something in water that is a stronger acid than the hydronium ion itself is, then we have complete ionization of that species in water. So that, and you notice here that the 6 that we have listed above the H3O plus ion here are the 6 that were listed as the strong acids right here. Okay. Now, there is a ranking of these in terms of strength, but you can't tell in water what that ranking is. If you took them and put them into a different solvent, such as ethanol, then you would be able to tell the difference between the strength of nitric acid versus hydrochloric acid and so on. Okay. But because we are very often dealing with water, we are essentially bracketed by the water itself and the hydronium ion. Okay. There are also, let's take a look at some periodic trends for acid and base behavior. So let's start over here where we have different elements that are from the periodic table that are connected to a hydrogen that could act as an acid. And what we see is that acid strength increases as we go across to the right, and it increases as we go down. and the base strength goes the other direction. Now, if we look at, say, methane right here, we say that the base strength is increasing this way. Why does this one say that methane acts as neither an acid nor a base? Anybody have an idea about that? Anybody in the chat have an idea? It can't accept any more hydrogens. That's right. And so let's take a look at CH4 and NH3 just for comparison. If we look at their Lewis structures, the difference we see is that the ammonia has a lone pair of electrons right here. So in order for something to act as a base, you have to have the ability for an H plus to add to the species, making a covalent bond. And so there is no lone pair on methane in order to accept an H plus. We can't make CH5 plus. So methane cannot act as a base. Now, it could act as an acid. It could donate a hydrogen, but it is extremely, extremely weak. It is so weak, in fact, that if we look at our list here, it essentially does not ionize at all in water. Okay. So this is one type of acid or base that we could have, where we have hydrogens or lone pairs on some element, a nonmetal, that we can either accept hydrogens or donate hydrogens. Another very common type of acid is where we have the hydrogen attached to an oxygen, an acid or a base, and then that oxygen is attached to some other element, and this may go on to have many other things attached to it. If you have a very low electronegativity element for E, such as a metal, then what you have is something like NaOH, which we know is ionic. And so this, what we call here bond A, breaks, and we end up with donating OH minus, and as a result, this acts as a base in water. If, on the other hand, our element E has a high electronegativity, so for example, if we have, let's say, ClOH, then this bond is very strong. The chlorine is holding on to the electrons in that bond quite a bit. And that shifts the electron density towards the chlorine away from the hydrogen. And so in that case, the hydrogen plus can come off, making this act as an acid. We'll get to this point in just a moment. If we have an intermediate electronegativity for E, so for example, one of the metalloids, such as aluminum, gallium, and so on, then it can be amphoteric. It can either break there or there. Now, let's take a look at this aspect right here. But to do that, we need to review a little bit of Lewis structures and talk a bit about accounting for electrons in our Lewis structures. So let's remember how we draw some Lewis structures. I'm going to start with sulfuric acid like so. Now, back in Chem 111, you were introduced to formal charges. I'm going to do formal charges in blue. And the idea of formal charges is that it is an accounting system for electrons in order to determine which Lewis structures are the best, or they contribute the most to the resonance structures of a compound. The way I do counting of formal charges is I imagine each bond line as having a dot on each end corresponding to the two electrons in the bond. And what we do to calculate our formal charges is that we start with what I call the core charge. So the core charge is going to be the nuclear charge minus how many electrons you have that are in the core, i.e. not the valence shell. And so this ends up, the core charge ends up being the same as the group number that we are dealing with. So if we look at hydrogen, it has a core charge of 1. If we look at oxygen, it has a core charge of 6. If we look at sulfur, which is in the same group as oxygen, it also has a core charge of 6. Okay. Now, we then subtract 1 for each electron, because an electron is negatively charged, to find out what the total charge on that atom is. And any electrons that are specifically on just that atom, you count for that atom, and the electrons that are in bonds get split equally between the two. That's why I have them, I envision each end of the bond as having one of the electrons in it. So the electrons in here, in this circle, are the ones that we assign to the oxygen. The electrons in here are the ones that we assign to the oxygen, and so on around. And so the sulfur would come around like here. So with this in mind, you can very quickly calculate out your formal charges. 6, 5, 4, 3, 2, 1, 0. This has a formal charge of 0. 1, 0, formal charge of 0. This one's identical to that one, so it's a 0. This one's identical to that one, so that's a 0. 6, 5, 4, 3, 2, wait, I didn't do this right. 6, 5, 4, 3, 2, 1, 0, right. This one's identical to that, and now our sulfur, 6, 5, 4, 3, 2, 1, 0, also 0. And so this Lewis structure has 0 formal charges on all of the atoms, which means that this is a very good Lewis structure for this compound. Now, a problem with formal charges is that this assumption that the electrons are being shared equally, that you split them in a bond, so the hydrogen gets 1 and the oxygen gets 1, is an approximation. The other extreme approximation you could make would be that whichever element is more electronegative is going to get all of the electrons that are in the bonds. So oxygen's more electronegative than hydrogen, and so you would assign both of those electrons to the oxygen. So I'm going to redraw our compound here. And this alternate accounting is useful for something else, and this is called oxidation number. So what we do in this case is we look at each bond and determine which element is more electronegative. Well, oxygen is more electronegative than hydrogen, and it's more electronegative than sulfur. So we would draw our circles like this for oxidation numbers. Okay? So using exactly the same counting system, just assigning all of the electrons to the more electronegative atom, we can count it up. So core charge of 1, no electrons, so this has an oxidation number of +1 on the hydrogen, +1. Oxygen has a core charge of 6, 5, 4, 3, 2, 1, 0, -1, -2, -2. 6, 5, 4, 3, 2, 1, 0, -1, -2. Sulfur, core charge of 6, no electrons, so an oxidation number of +6. So what we have here now is two different ways to assign charges within the molecule. The formal charge method is useful for determining which Lewis structure is the best Lewis structure. The oxidation number method is useful to get a sense of the electronic environment of the elements, and for doing what's known as redox chemistry, which we are going to be ending this semester with later. So we are going to be coming back to this idea of oxidation numbers later in the semester. Whereas reality, well, reality is kind of halfway in between these two. So these are two different kinds of approximations you can make that we use for different things, and reality is somewhere in between the two. So with this in mind, I'm now going to draw a related compound to sulfuric acid here, which is known as sulfurous acid. Like this. And if we look at our oxidation numbers here, we find that we still have +1s on the hydrogens, -2, -2, -2 on the oxygens, and the sulfur here, instead of being a +6, is a +4. Okay. So what we have here is very similar compounds, but where the sulfur is more positive in this case than it is in this case. And so let's think about that with relation to this structure here. The more positive the sulfur is, the more it is going to be pulling the electrons in towards itself. The more these electrons are going to be shifted in, and the more acidic these hydrogens end up becoming. So sulfuric acid here is a strong acid for both hydrogens. But in the sulfurous acid here, because it is not pulling in quite as tightly on those electrons, is a weak acid. And so what we can do in comparing different types of oxyacids like this, we can determine which are stronger than the others by looking at the oxidation state of the central atom. So there's a question here. The best Lewis structure is the one with 0 charges. Yes, so if you can get it to completely have 0 charges, that's the best oxidation state, that's the best Lewis structure you can have. If you are not able to get it to everything having zero charges, then the lowest charges possible would be the best one. And if you have to have charges, putting the negatives on the most electronegative atoms and the positives on the least electronegative atoms, that would be the best Lewis structure that you would have. So I suspect that was covered in Chem 111, but it's been a while since we've talked about that sort of thing, so this is hopefully a review for that. So let's take an example here and look at a couple of other compounds. So we're going to look at nitrogen. Let's see, I'm going to do HNO here. Okay. So this here is nitric acid. This is nitrous acid. Okay. So the first thing to do, what I'd like to see you try to do here, first practice determining formal charges for both compounds, then determine oxidation numbers, and then from the oxidation numbers, tell me which of them is going to be the strongest acid. And so I'm going to let you work on that a little bit. So there's a question on the chat. To recap, you just said you can look at the central atom and see which is most positive for the strongest acid. Yes, that is correct, which has the largest positive oxidation number. And this is specifically for oxo acids where you have have oxygens attached to the central atom. Okay, let's look at nitric acid here. I'm going to first put in formal charges just as some practice. What's the formal charge on the hydrogen? Chat says a +1. I'm not asking oxidation number at the moment, I'm asking formal charge. So remember, formal charge is where you split the electrons equally in a bond, and that's correct, 0. What's the formal charge on this oxygen, the top oxygen? Also 0, correct. What is the formal charge on this oxygen? Also 0, correct. What is the formal charge on this nitrogen? +1, that's right. What's the formal charge on this oxygen? -1, that's correct. Okay, so here is an example where we are not able to get all of the electrons, all of the formal charges equaling 0. The reason for that is that what we would like to do in order to get them to be 0 would be to take 2 of these electrons and make a double bond to the nitrogen, but then we would be exceeding the octet of the nitrogen as we do that. And while we can do that for sulfur here, because sulfur is below period 2, nitrogen is in period 2 and cannot expand its octet. Okay. So now let's look at nitrous acid. What is the formal charge on hydrogen? 0, correct. Formal charge on this oxygen? Also 0. Formal charge on this oxygen? Yep, 0. Formal charge on this nitrogen? Also 0. Excellent. Okay, now let's do oxidation numbers. And so oxidation numbers say that the electrons in bonds go to the more electronegative element. So which is more electronegative, oxygen or nitrogen? Oxygen, that's right. So what is the oxidation number of the hydrogen here? +1. What is the oxidation number of this oxygen? -2. Oxidation number of this oxygen? Also -2. Oxidation number of this oxygen? Also -2. And oxidation number of this nitrogen? +5. Right. Over here, oxidation number of this hydrogen? +1. Oxidation number of this oxygen? -2. Oxidation number of this oxygen? -2. Oxidation number of this nitrogen? +3. Excellent. So, which of these acids is going to be stronger, nitric acid or nitrous acid? Nitric, exactly right. And in fact, nitric acid is a strong acid and nitrous acid is a weak acid. Okay, so that is the idea of how to gauge relative acid strength of two related acids. Okay. Two other really brief topics before we get to buffers. Most metal ions, so Al3+, Fe3+, Cu2+, Zn2+, those are just some examples. If we dissolve these in water, the water becomes acidic. What is happening when this happens is that these will get associated with water molecules, making coordination complexes, and so on. Many of these, so the copper, the aluminum, and the iron we'll get 6 of them that associate with it. And so the whole thing here is going to have a 2+ charge. The zinc, only 4 of them associate with it. And when this happens, it changes the acidity of the hydrogens that are part of the water here. And so this can be in an equilibrium with CuH2O5OH plus and H+. So it can act as an acid. You can certainly imagine multiple hydrogens coming off, one from here, one from here, one from here, and so on. But generally, only the first one it comes off to an appreciable extent. These are all weak acids when this happens, and generally the ionization increases as the charge on the ion increases. So 2+ versus 3+, the 3+ will typically have will typically be a stronger acid. And as the size of the metal ion decreases, so the smaller the ion is, the more acidic the waters tend to be. That in a lot of cases, the actual equilibrium constant is not well known. There are a few cases in the text that where they are known, and I think these four are four that are known. The last sort of random acid-base topic is about polyprotic acids. So we looked already at sulfuric acid here as being as having two hydrogens that can ionize off. This is the only example of a strong polyprotic acid where both of the protons are strong acids. There are plenty of polyprotic acids though, so we can have H3PO4, for example, and all three of the hydrogens are acidic. So there is an equilibrium of this with H2PO4 minus. We'll do plus H2O plus H3O plus. This can now act as an acid, H2PO4 minus plus H2O in equilibrium with HPO4 2 minus plus H3O plus, and then HPO4 2 minus plus H2O is in equilibrium with PO4 3 minus plus H3O plus. So this is phosphoric acid, and each of the protons can act as an acid. All three of these are weak acids, and generally the equilibrium constants, we'll call this K1, K2, K3, generally there are orders of magnitude differences between these. So K1 is much greater than K2, is much greater than K3. Typically, typically this difference is somewhere between a factor of 100 and a factor of maybe 10,000 between these. And what that means when they are this different is that usually you only need to be dealing with one of these ionization steps at any given time. And so either this one is the only one that matters and there's almost none of these two happening, or this has completely gone to this side and then you only have to deal with the second one or something like that. So as long as the difference is at least a factor of about 20, if the difference is more than a factor of about 20, then you typically only need to deal with one of them at a time. And for polyprotic acids, it is almost always much larger than 20. So let's see. So that's going to be all of the acid-base stuff before we get into buffers. Does anybody have any questions on any of this material before we dive into our next big topic? Okay, let's talk about buffers. What we're going to do is we're going to start by looking at acetic acid. And so that is CH3COOH. Its acid reaction is this. Okay. We are going to make a sample. we are going to deliberately make it so that we are adding acetic acid to make enough acetic acid to make it 0.1 molar here, and we're going to add enough sodium acetate to make it 0.1 molar in this. And we're going to say this is approximately 0 initially. So, so by preparation, we are starting with 0.1 molar acetic acid and 0.1 molar sodium acetate. Okay. The equilibrium is going to have to shift to the right because we're assuming that that's starting close to 0. So x minus x, 0.10 minus x, 0.10 plus x, and x. Now, we also know that the equilibrium constant for this reaction is 1.8 times 10 to the minus 5 molar. So let us now assume that the x is going to be small compared to the 0.1, and we'll check that in a moment. So that means that we have 0.10 molar times x over 0.10 molar. Those cancel. And so we find that x equals 1.8 times 10 to the minus 5 molar, which happens to be the Ka value we had. And we see that that is indeed tiny compared to 0.1. And when we calculate the pH from this, we find the pH of this sample is going to be 4.74. So this is a negative base 10 log of 1.8 times 10 to the negative 5. This sample that we just made, we are going to call a buffer. Okay. And we'll explain what that means in a moment. Is there a reason I started with 0.1? I will explain why I did that in a moment. Yes, there is a reason I started with 0.1. But what I want to do is compare this buffer with a sample that does not have this equilibrium going on, but we've made the same pH to it. And we're going to compare those two samples. So here we have a pH of 4.74, and here is our concentration of the hydronium ions. Our non-buffer, we are going to add 1.8 times 10 to the minus 5 molar HCl. Because HCl is a strong acid, it is going to have exactly the same, it's going to dissociate completely and will have exactly the same hydronium ion concentration as the HCl concentration. And so this non-buffer sample is going to have the same pH that we have for our buffer. Okay. Now what we are going to do is we are going to do the same things to the non-buffer and the buffer and see how it responds to the perturbations that we are applying. So starting with our non-buffer, let's say we start with 100 milliliters of this, and we are going to add 1 milliliter of 0.1 molar HCl. Okay. So at that point, we have 1.8 times 10 to the minus 5 moles of H plus from this, plus, no, I'm sorry, that's moles of H plus per liter of solution, times 0.1 liter to find out how many moles of hydronium ion there are in the 100 mils we started with. Okay, so we end up with 1.8 times 10 to the minus 6 moles of H plus in our 100 milliliters. We are now also adding to it 1 mil of 0.1 molar. So we are taking 0.1 moles H plus over 1 liter times 1 milliliter, so 0.001 liters to get, this is now 1 times 10 to the minus 4th moles of H plus. We add these two together, and so we have 1.018 times 10 to the minus 4 moles of H plus once we've added those together, and we have it now in 101 milliliters of solution, or 0.101 liters of solution. We calculate that. 1.018 divided by 0.101 gives us, oh, I didn't do the times 10 to the minus 4. Times 0. So that gives us 0.001 molar. Let's do the base 10 log of that. And so we get a pH of 3. So we started with a pH of 4.74. We added 1 milliliter of a concentrated acid to it, and we ended up with a pH of 3. So our pH changed by 1.74 units. Now, we want to do the same thing to our buffer solution instead. So in this case, we have an equilibrium we have to worry about. So we have I'm going to draw out the ice table. Probably the easiest way to do this would be to start with 0.10, 0.10, and now we are going to actually, we are changing our volume, so we need to take that into account. So our 0.10 here is going to be 0.10 times 101 milliliters over 100 milliliters. So 0.1 times 101 divided by 100 gives us nope, we need to do it the other way around. I have it backwards. 0.099. So 0.099, 0.099. And we are adding the same amount of H3O plus that we had before. What we, so we have 1 mil of this. We now are going to, so we have 1 times 10 to the minus 4 moles of the H plus. This is now in our 0.101 liters. And so take 1E4, change sign, divided by 0.101. And we have our H plus that got added in is 0.00099 molar. Now, the easiest way to handle this is to do a pre-shift like we did before. So we're going to subtract the 0.00099 from each of these. So shifted initial, change, equilibrium. So 0.099 minus 0.00099, 0.09801. Oh, no, that's this one, 0.09801. 0.099 plus 0.00099 gives us, excuse me, 0.0999. And this goes to 0. Now, minus x, x, x. This is just going to be our 0.09999, 0.09801, x. We now have our equilibrium constant. Ka, 1.8 times 10 to the minus 5 molar equals 0.09801 times x, it's molar, 0.09999, and we solve for x. So 1.8 times 10 to the negative 5 times 0.09999 divided by 0.09801 gives us an x of 1.836 times 10 to the minus 10 to the minus 5 molar. So let's find our pH. Our pH is now 4.736. So the point here let's take a step back and think about what's going on. We made a buffer, and I'll explain what makes this a buffer in a second. And we did it by having an equimolar amount of acetic acid and its conjugate base, and we got a pH of 4.74. We made a non-buffer sample with the same pH as this, just by adding a little bit of HCl to it. Okay. To each of them, we added 1 milliliter of strong acid, and we looked at what happens to the pH when we do that. For the non-buffer sample, our pH changed from 4.74 to 3. So the pH dropped by a lot, by 1.74 units. We add the same amount of acid to the buffer, and we find that the pH shifts only down in the third decimal place, in the second decimal place, in the third significant digit. It changed from 4.74 to 4.736. So the idea here is that Le Chatelier's principle was taking effect. We had our sample, started with equal amounts of this, and then we added H3O plus. And that shifts the equilibrium this way, reducing the amount of H3O plus that's present. And so what that means is that for this system, because there is an equilibrium between these two, the hydronium ion concentration barely changed at all. That's what a buffer is. That's what a buffer does. We could do the same calculation by about adding base to the system. And in that case, we added base, then the equilibrium would shift the other direction. And so if we were to plot what happens to pH as we add, say, H3O plus, for a non-buffered sample, the more you add, the more the pH is going to go down by a lot. But for our buffered sample, it's barely going to change. There's a request to explain the second ICE table. I will absolutely do that in just a moment, but I want to emphasize the point of what we're doing here. So blood, for example, blood is a buffered sample because it has an equilibrium between carbonic acid and bicarbonate ion. And blood, as a result, has a pH of about 7.4. If the pH of blood ever got down to about 7.1, you would die. So this buffer that is part of your that is part of your blood prevents you having major changes in the pH of your blood. So the request to explain the second ICE table. Okay. So the first thing I did was I calculated what the concentrations of I just took the top line here and I corrected the concentrations to take into account the fact that our volume has changed, because we started with 100 milliliters of the buffer, and we added 1 milliliter of the acid to the buffer, so that dilutes each of those by a little bit. Okay. Then I said, okay, what is the concentration of the hydronium ion that was added to the sample in that 1 milliliter of acid? I then said, let's pre-shift the equilibrium as far to the left as possible to make our math easier. So I took this value and added it to this. I took this value and subtracted it from this. And so we then have our shifted initial, minus x plus x plus x for the equilibrium line. We are assuming, which we then prove, that the x is going to be small compared to these two values. And so then we can calculate what the hydronium ion concentration is very simply without even having to solve a quadratic. So, let's take a look at our acid equilibrium constant. I'm going to take this expression and I'm going to solve it for the H3O plus. Well, we have H3O plus on this side. I'm now going to take the negative log base 10 of both sides so that we can get pH on this side. So negative log base 10 of H3O plus equals negative log base 10 of Ka HA or A minus. Okay. So this side here is pH. When you have things that are multiplied together inside a logarithm, you can then add, treat it as the sum of logs. Oops. Okay. So the negative log base 10 of Ka is the pKa minus a log base 10 of this would be plus the log base 10 of that flipped. And what we have here is known as the Henderson-Hasselbalch equation. I may be misspelling this. I believe it's BALCH, the Henderson-Hasselbalch equation, which is an extremely convenient way to calculate the pH of a buffer system. So you'll notice that when I created the buffer, I started with equimolar amounts of the conjugate base and the weak acid. What is the log base 10 of 1? Because if it's the same concentration of both of these, then that ratio becomes 1. What's the log base 10 of 1? 0, correct. And so the pH of that system equals the pKa. And you'll notice that when we first solved this, we found that exactly that is what happened. That we had the Ka right here, which became just the concentration of the hydronium ion. So the pKa was 4.74 for acetic acid, and so that became our pH of an equimolar buffer. So what this means is that we can generate a buffer at any pH we want if we can find a weak acid that has a pKa of roughly the pH we want to make. Then when we deviate from equimolar ratios, we can calculate the pH just by changing our concentrations of the acid and the HA right here. So if we go back to this equation here and look at our shifted initial values, so we want which one in the numerator? The A minus in the numerator. So if we want 0.09801 divided by 0.09999, we have that ratio. We want log base 10 of that, and we add that to our pKa, which was 4.74, and we get 4.7313, which is very, very close to what we got right here. So this Henderson-Hasselbalch equation lets us determine the pH within the limits of small changes of x. It lets us determine our pH of a buffer system even after we have applied changes to the system by adding in some extra acid or some extra base. Okay, so there's an important concept within buffers known as the buffer capacity. So when we think about the equilibrium going on here, the buffering action is going to work up to a point as the equilibrium will shift in response to extra acid that is being added. But at some point, you're going to start to run out of your acetate ion. At that point, once you start to run out of that acetate ion, you have exceeded the buffer capacity. So typically, the buffer stops being useful when one component is 10% or less of the other component. It's just sort of a rule of thumb about that. And so once that happens, then at that point, the pH will start to change more dramatically, similar to what happens if you were adding acid to just water. So what do I mean by a component? Right, what I mean by the component is that the two active parts of the buffer are the weak acid here and the conjugate base of that weak acid here. So if one of these is 10% or less as compared to the other one, then the buffer is not will stop working as well. So if this here were 0.1 molar, and if this here were 0.01 molar, then it's not really buffering anymore. Okay. So when I get the small group activity out to you folks, it's going to be dealing with some of these kinds of ideas as it relates to something known as the alkaline diet. The alkaline diet is a diet fad that is about, alkaline means basic, means base. It is a fad about where you are essentially trying to lower your body's pH. And a problem with trying to do that is that your body is buffered. Your blood is buffered, the various different kinds of components in your body are buffered. And so what I'll have you working through in that small group activity will be some examples of calculating for components of this diet, how much of an effect that could even possibly have on the pH of your system, of your blood, of your digestive tract, things like this. And so these are things that can be calculated using ICE tables, or in some cases more conveniently using the Henderson-Hasselbalch equation. And what we're going to find is that the alkaline diet actually has essentially no effect at all on your body's pH. Okay. Any questions on buffers? Did the general idea of what a buffer does and why it works, is that making some sense? The group activity this week or next. So I will get it out this week, so and it won't be due until next week. All right, any, no clarifying questions on buffers at this point? All right, thank you very much, everyone. Tomorrow's class is going to be a duplicate of today's class, so if you sat through this one, you don't need to sit through that one. And on Wednesday and Thursday, we will be addressing questions off of Piazza. Thank you all.